Alrighty, let's get started. Sign-in sheet, get that passed around. Okay, just so everybody's aware of a few quick announcements. So let's talk about housekeeping between now and the end of the semester. Okay, so you all currently have homework 6, which is on steel and aluminum. Okay, you have that homework that's due on the Thursday after we get back from break. We're going to talk about aluminum today, but I'm really going to talk about it for about 5 minutes because there's really not a whole lot to say because we really don't use it very much in civil engineering applications. I just want to go over the properties. If anything, after today, you'll have an understanding as to why we don't use it. And the simple answer is in structural engineering applications, aluminum is weak. It just does not have the necessary modulus of elasticity and what have you in order to resist the loads that we need these materials to. So we don't even really use it that much. So you have homework 6. That's going to be due the Thursday after break. You are going to get one more homework assignment, which is going to be basically on timber and on asphalt. We'll talk about asphalt after break, and you'll get one more assignment that'll probably be due sometime during dead week. It'll probably be pretty short. Your final assignment, the big lab report, is due Tuesday, December 5th. Okay, so let's talk a little bit about that. Okay, so I posted 28-day cylinder testing for mix 1 right after lab last week. On Thursday, we will do 28-day cylinder testing for mix 2. Also, next week, you need to bring your beam data because we're going to collate not just last week's beam data, but this week's beam data, and then you'll have all of it. Okay, and that'll give you plenty of time to put together your report between now and December 5th. Sound good? Now, well, they better. Now, has everybody gone through and checked your data on your data sheets to ensure that it's accurate? Nope, because I had a student who caught a couple errors. So who's in group 4? Okay, who's in group 5? If you shook your head and said, yeah, we checked it. No, you didn't. Okay, this is the Excel sheet, and if we look here on 14-day mix 2, I don't think those are right. Okay, we checked it. We checked it.
I think that's right.
All right, well, okay, so group 4, was it 60390? Now, hold on. Probably. Do you have your data sheets group 4? There's enough of you in here that one of you should have your data sheets. This is 14-day, this is mix 2, and this is cylinder number 2. So this is 60770. And this is 60390. Okay. All right. No, I know he did. I wasn't testing him. I was testing everybody else who said, "Oh yeah, we checked it. We checked it." I know he checked it. I was calling everybody else on. That's what I was doing. So I at least got groups 4 and 5, so. It was a little bit. Okay, so the only data we have left to collect are 28-day cylinders for mix number 2, and then our cylinder data is done, and we'll collate beam data on Thursday, and then that's it, okay? So, everybody good on that? Does anybody have any questions about the final homework? I do want to keep bringing it up because I know you're like, oh, it's not due till December 5th. It's tempting to put it off till the last minute. I'm telling you, don't do that, okay? It is November 14th, and it's due December 5th. I know that seems like a long way away, but Thanksgiving break is creeping up, and you have no guarantee that your folks are going to be around. They might be off in, Banff, Canada, fishing and not anywhere near here, and then you come back and you only have 1 week to put together a lab report that's going to be on the order of 50, 60 pages, and that's not even counting pictures. So Have you all started on it? Okay, good. All right, so any questions? Possible. I mean, you got graphs, you've got tables, and I'm talking about the pictures that you took in the lab. I mean, that's possible. No, not straight text, but formulas, calculations, charts, all that.
How much do you really want to read?
I'm only going to have to read 6 of them.
It's really not that bad.
You're right. What he said. He said it's not that bad. And you all know, all right, the big thing to pay attention to, all right, guys, the big thing to pay attention to is that rubric. Okay, there's a rubric that was posted online that literally that's how I'm going to grade the report. So you need to be paying attention to that rubric and ensuring that all of the information that it's asking for is included. Here, I'll pull it up just to make sure everybody's on the same page. So this is the rubric, and this is what I'm going to do. So, cover page 6 points, table of contents 6 points, introduction, test procedures, conclusion, sources of error. Oh goodness, go away. Yeah, we haven't had the Java pop up yet. Give it time, it will. Graph. I love this computer. Graphs, data reduction and calculation, sources of error, references, appendices, the understanding of the lab. This isn't a section of the report, by the way. This is me evaluating whether or not you understood the lab. So I know there's going to be one group that says understanding of lab. It's like, no, that's not what that is. So yeah, this one is me giving my assessment of your lab report. That's what this is. So, okay. So make sure you're following this. All right. Any questions? Okay. So let's go into lecture. Like I said, I've got 2 real topics I want to talk about today, aluminum and timber. Aluminum is going to be real quick. There's really not a lot to say. The notes and everything are posted. I got those posted today. I usually like to post them a little earlier, but I've had a busy week. But there's really not a lot to say about aluminum, and here's why. So first off, I mean, I think everybody here knows how abundant aluminum is on the planet, and it's used for quite a lot of engineering applications. But one of the things you'll find is that it's not used very much for many civil engineering applications. You don't really see very many aluminum bridges. You don't really see very many aluminum building frames. I mean, you see aluminum Coke cans and aluminum products used in mechanical engineering in cars and planes and all that stuff, but you really don't see it very much in civil engineering. There's a very specific reason why, but we'll get into that. First off, it's expensive in comparison to other materials. It also has some very interesting aspects. So first off, lower strength. Okay? If you just look at yield strength and tensile strength of aluminum and compare that against just regular old mild carbon steel, it doesn't hold a candle to it. It also, in terms of ductility as well, steel has a much higher ability to withstand permanent deformations than aluminum does. One other aspect of this is a coefficient of thermal expansion. And we'll bring up a little bit of mechanics of deformable bodies for you all that love that class so much. When we apply mechanical stresses to a system, it responds by deforming. So I take an element, I physically yank on it, and it will deform. What is another easy way that I can cause deformation on a given system? I can heat it up, or I can cool it down, right? When things heat up, they tend to expand. When things cool down, they tend to contract. In solid mechanics, we relate that through a coefficient of thermal expansion. Okay, so the idea is that each material, just like each material has its own Young's modulus and its own Poisson's ratio, The coefficient of thermal expansion is another intrinsic property unique to a given material. For instance, those of you who might remember this from deformables, if you want to determine, let's say, the change in length of a bar that's been heated up some amount, you take the length of that bar, you multiply it by the change in temperature, so if it goes up 70 degrees or 80 degrees or what have you, and then you multiply that by your coefficient of thermal expansion, which is alpha. Okay? I know you saw that in deformables. I know you did. Okay? So alpha is a property that is unique to a given material. So the alpha value for steel is different than the alpha value for aluminum or different than the alpha value for brass. Aluminum has a coefficient of thermal expansion that's about twice that of steel. So if you take a piece of steel and you sit it outside, you're going to get twice as much strain essentially in the aluminum that you will in the steel under the same thermal conditions. And that's a big deal since a lot of our civil engineering structures are outside. So that's one reason why we really don't use aluminum that much. But we do use it a lot for other industries. I mean, you'll use it for obviously containers and packaging, Coke cans, and what have you. You do use it for aspects in engineering that aren't very load-bearing. So like architectural aspects, like doors and windows and siding. Nothing wrong with that being aluminum because they're not really experiencing a significant force effect. That's no big deal. Sometimes they're used as electrical conductors, and you also see it used quite heavily in aircraft vehicles and things like that. Now, it does have some advantages. I mean, it's light. It has a good strength-to-weight ratio. I mean, you got to give it that. It's got good properties. Has good weldability properties. It doesn't really rust. I mean, there's a little bit of corrosion that can happen with aluminum, but not to the degree that you get with steel. So that's kind of nice. It works well for cast products as well because of its melting point. It's a little easy to deal with. Its disadvantage, the big one, is its modulus of elasticity. It is 1/3 essentially that of steel. So if I take a product, if I take a steel product and aluminum product, exact same dimensions, exact same properties, except for one's made of steel and one's made of aluminum, and I apply a tensile load to it. Say I take a steel bar and an aluminum bar and I yank on it, assuming they have the same dimensions and the same forces and what have you. The aluminum bar's deformation will be 3 times that of the aluminum bars will be 3 times that of the steel. So that's a big deal in the world of engineering. Take highway bridges, for instance. One big controlling aspect of a highway bridge design is limits on its deflections. Okay? A common limit in highway bridge design is L/800. So if I take the length of a bridge, okay, so you all have calculators. Let's say I have a 100-foot bridge, simply supported. Okay? Take 100, divide it by 800, and then multiply it by 12 because I want my answer in inches. 1.5? So under live load, and by live load I mean the vehicles, the HL93 ASHO design truck, you folks in structural analysis should know what I'm talking about. Right? Under that vehicular load, a 100-foot bridge in the United States cannot deflect more than 1.5 inches. So a material's ability to withstand those deformations is really important. It's one of the reasons why aluminum doesn't really work that well. If you look at tensile properties, I mean, again, if you compute the stress of this, compute the slope of that linear portion, it's going to be about 1/3 of that of steel. I mean, the modulus of elasticity is about 10 million psi for aluminum. What's the modulus of elasticity for steel? Well, 29,000 ksi, or how many psi? 29 million. Okay, so that's where we're getting the 3 times that. Tensile strength, we're looking. I mean, again, we're looking pretty low. So if you're a couple other things with aluminum, because aluminum tends to be used for aircraft type products and things like that. I mean, aluminum can be bolted together, but you tend to see more riveting applications with aluminum than you would with steel. You have to protect those elements against corrosion, so sometimes you have to galvanize them or aluminize them or what have you, just to ensure that you don't get significant corrosion. Speaking of corrosion, so aluminum, it kind of corrodes. It develops kind of a thin oxidation layer on the outside, and that's about it. It's kind of like an oxide film. It actually serves as a protection barrier for the rest of the product. Certainly, regular old structural steel doesn't behave that way. Weathering steel kind of does, because it's the chemistry of that heat of steel is actually designed in order to behave that way. So one big issue, though, is if you have a significant presence of water, you can get a little bit more corrosion. So that means painting it, keeping it dry, providing some sort of insulator, et cetera, et cetera. That's really all I have on aluminum, because, again, we don't really use it much in civil engineering applications. Yes? You see aluminum products riveted, especially like in the aircraft industry, you see aluminum products riveted a lot more. So. It's just an industry standard for, I mean, keep in mind, I'm not talking about civil engineering applications. I'm talking about like aircrafts and you know, vehicles and things like that. That's a mechanical engineer's world. Remember, mechanical engineers design weapons. We design targets, so. Did you like that? Yes. Okay, this is recording. I'm glad you whispered that. It doesn't need to have my name associated with it. Next thing you know, I'm going to get a knock on my door. It's going to be like, we got some questions for you. No? Should I have? You're right. I probably do. I need to sanitize each of these videos, right? You can get corrosive, how can I put this? It increases the susceptibility of corrosion if they're in contact with one another. I generally would not allow them to be in contact with one another. And also, but again, not to keep harping on the issue, but generally we just don't use aluminum that much. So now let me also say this. If you had two galvanized products, that wouldn't matter, because it's not the two constituent materials that's coming into contact. It would be galvanizing and galvanizing. So there's really zinc and zinc. And there's nothing wrong with that at all. So. You might have some corrosion, but I'll say this. Usually that siding tends to have some sort of coating on it. So yeah. It's really more your connectors that you have to worry about, because that's where you've got holes and you can collect water and things like that. So. Any other questions? Let's see. I don't really have much to say on aluminum. I even wonder why we should even talk about it. So, but the more you know, knowledge and youngins and all that. Okay, so let's talk a little bit about timber and wood. I'm using a little bit of an older set of notes just because I did not have time to do a little bit of reformatting on this, but it doesn't matter. These are great notes. So let's talk a little bit about wood. Let's talk a little bit about timber. Wood is the earliest construction material that we ever used, right? Historically, okay? I mean, the first construction project in history. Have a river, there's a tree, knock the tree down, it goes over the river. You have a bridge. First construction project ever.
I'm just going to design all my bridges that way.
What's that? A what? You know that if you go to MIT, the mascot for MIT is the beaver because they're nature's engineer? I'm serious. I'm not making that up. Hey, I went to Bluefield High School. You know who the mascot for Bluefield High School was? The Beavers. So I take exception to that, thank you. What's that?
I said, did you all have a lot of engineering at your high school too?
No.
It's not as clever then.
No, it's not. Not even close. I totally agree with you. I mention aluminum because, I mention timber because while timber is not very common for civil engineering applications, it tends to be used quite a bit in secondary civil engineering applications. And what I mean by that is this. So if you're designing, let's say, a building, okay, and that building is going to be, let's say, a steel frame structure, and you're going to have, let's say, concrete floor slabs or something like that. Commonly, you would use like a stay-in-place metal formwork for that for the slabs, but it's very possible that you would use wood to form up your concrete. Wood is a very common construction material used to form concrete. Okay, so so in large-scale civil engineering applications, it is still used quite prevalently for those types of applications. Now, wood is obviously used a whole lot in the residential market, right? 2x4s comprise the primary construction material we use in residential construction, right? 2x4s, 16 inches on center, that frames up your walls that will ultimately frame up your house. So an understanding of how wood behaves and how timber products are produced and the different timber products that are out there is worth discussing, okay? Now, let's talk a little bit. Let's just go back to basics. It might feel a little bit like we're in 7th grade when we're talking about some of this. So some of these terms you might be familiar with, some of them not. So I have, how many of you have heard the difference between a deciduous tree and a coniferous tree? Anybody know what I mean? So help me out. What's the difference? There we go. Yeah, deciduous trees lose their leaves. Coniferous are pine trees, evergreens that essentially don't. They retain their color. They're evergreen. They retain their color throughout the year. Yes, that's what that means. How many of you have heard of the terms endogenous versus exogenous when it comes to trees? Oh, I got you on something. Good. Okay, so we in most engineering applications use exogenous trees. And what that means is that's talking about the way that trees grow. Now, up until now, how did you think trees grow? Annually, and they form the rings, right? That's what an exogenous tree essentially means. That's what most trees are, and those are the trees that we use for most engineering applications. They grow on an annual basis, they form annual rings, and they grow from the inside out, okay? Endogenous trees don't really grow like that. The fibers don't really grow in an outward direction as much as they kind of intertwine and develop along the tree. You get very strong and lightweight properties, but they're a little bit variable and they don't really work very well for engineering applications. A very good example of an endogenous tree is a palm tree. Okay, palm trees really don't grow like that. They kind of do this whole thing. So I can't really do it. So that's all you got. Okay. Let's talk a little bit about the structure of wood. So I'm sure everybody now knows you can determine the age of a tree. If you have it sawn, if you're looking at the stump, you can count the age of the tree by counting the number of rings, right? I'm sure everybody knows that. So if it's got 57 rings, it's a 57-year-old tree. Just so everybody's aware, like what comprises a ring, if you look at the rings of a tree, you see sort of light regions and dark regions. It's not as if that's really different wood per se, but it's really more of a density of the individual cells of your wood. So to differentiate between the two, so if you look at your rings, you sort of have a lighter grained wood and then a darker grained wood. Those darker grains correspond the denser regions of thin-walled cells within your tree. Okay, early wood, that is your rapid growth right after winter. That's as soon as the winter ends and you get into spring, you get a sudden bloom of growth during the spring. Once you get into summer and it starts to get a little warmer and then it starts to cool down, that growth tends to slow down a little bit, and then you develop late wood. So in those slower growth periods, the growth occurs over a denser region. So that's why you have denser collection of cells. Everybody okay with that? We're good? Okay. All right. So some structural features of trees so that you all understand a little bit about the anatomy of a tree. So I'm starting at the center. I'm going to work my way outwards. I have a feeling probably like in middle school or high school, you probably learned these terms before. Like how many have heard of the pith of a tree, the center core of a tree? Okay, so a lot of you probably seen this before. The heartwood is right outside where the pith is, and then you get your sapwood. The sapwood is really what transmits the sap throughout the remainder of the tree. You have a very thin cambium layer, which is really where all your wood growth occurs. It grows on the outside out, so the cambium is where the wood is growing. And then you get into your bark, your inner and outer bark. And your outer bark is essentially that dead sort of corky type layer that exists on the outside and insulates the rest of the tree. Everybody okay with that? Okay. Now, I'm going to throw some words at you. Some words that I'm pretty sure you haven't heard before. How many of you have heard of the term isotropic? Okay, now how many of you know what that term means as it relates to engineering or engineering materials? Okay, let me explain. All right, so let's say I have a little cube of steel, okay? Cube of steel, okay? So we'll say it's like 3 inches by 3 inches by 3 inches. And I take that cube of steel and I press on it, okay? So I'm putting it in compression. Steel tends to behave very isotropically. We tend to assume that steel is an isotropic material. And the reason why is it really doesn't matter if that cube is faced this way or this way or this way. Steel, from a material standpoint, the properties of steel really don't change with the orientation of my load. Does that make sense? Now, don't get me wrong. I don't want you to confuse that with just general structural behavior. For instance, if I have a W10 by 49, which weighs how many pounds per foot? There we go. There we go. How deep is a W10 by 49? I was asking him. I'll ask you next time. All right, but going back to, all right, let me make sure everybody understands this, okay? If I have a W10 by 49 and I take that W10 by 49 and I yank on it and I apply tension, it tends to fail by either some degree of yielding or some degree of fracture. But if I take that element and I press on it, it will fail by buckling, right? It will be in compression and it will lose its stability. But that's it. Those failures are a function of the element's geometry. How big is it? How long is it? Etc. From a materials aspect, the actual material really doesn't behave that differently in one direction or another. I mean, if we're getting technical, like really technical, I mean, steel does have slightly different properties in the direction of rolling as opposed to perpendicular, but not enough for us to really have to consider them in most civil engineering applications. That is an isotropic material. An anisotropic material is a material that has different properties in different directions. Wood is a very anisotropic material. Specifically, if we're talking about, let's say something like a 2x4, and let's say we're talking about its tensile strength, how much it can withstand when it's being yanked on. Wood tends to be a lot stronger when you apply its load parallel to the grain. Perpendicular to the grain in tension, it's a lot weaker, okay? Make sense? Wood is a very anisotropic material. A lot of times, we can assume wood to be what's called orthotropic, okay? Orthotropic basically means that its properties let's say this way, are different than its properties this way. And by the ortho, I'm sort of talking about 90 degrees. That's not really true because we're really talking about longitudinal, and we're talking about tangential and radial directions. But for something like a 2x4, that's a pretty safe assumption. That's a lot of times how our limiting stress values are reported. We're talking about tensile stress parallel to the grain, tensile stress perpendicular to the grain. That's a really orthotropic view of how wood should behave. Okay, does that make sense? Everybody okay with that? So wood tends to be a very anisotropic material. I'm going to pop quiz you on something. What do you think about concrete? Tell me, do you think concrete, how would you assume concrete behaves? I can't hear you. Somebody. What's that? So we've got anisotropic. How many people say? Surprisingly, I'll say this. Now, concrete is a material that behaves very differently in compression than it does in tension. And we understand that, all right? I'm curious, how many of you have taken your beam data from last week and back calculated a modulus of rupture? Has anybody back calculated a modulus of rupture?
For what class?
It'll happen. It better. I mean, I got no problem, zeros are fine with me. It's actually less effort to do a 0 than it is a 1, 0, 0. It's less pen strokes. Then somebody said, what about just doing a check mark? There's no numbers associated with that. We're engineers.
I'll get a 1 on it.
I didn't say that. And are you sure you want me to say that? Okay. Okay, let's move on. Okay. One of the things that really affects wood properties.
No, I mean seriously.
Oh, that's a good question. Oh yeah. No, that's a good question. I was like, well, wait. Where have you been? No, I'll say this. Okay. Concrete is a material that behaves very differently in compression than it does in tension, and we understand that. However, if I have a cube of concrete and I load it this way versus turning it and loading it this way, or turning it and loading it this way, honestly, its behavior really isn't going to be that much different. Now, let me also say this, okay? And here's one big difference between characterizing a material like steel and characterizing a material like concrete. Okay, steel we can tend to assume is a very homogeneous mixture. Okay, what I mean by that is steel, its consistency for the most part tends to be the same throughout its cross section. So if I had a cube of steel, it's basically the same properties here as it is here, as it is here, as it is here, etc. Concrete is a very heterogeneous material. In other words, it's a mixture of gravel and sand and cement and water, so its properties are highly variable. I mean, concrete properties here might be different than they are here. I mean, you all have even seen that in the lab, right? If you didn't properly rod it or you didn't properly tamp it, give it the old tappa on the side, right? Just tap it in, tap-a-roo, right? So, but if you didn't do that, you can create a weak spot, right? It's your home. Go into your home. Price is wrong. No, sorry. Price is wrong. All right.
So isotropy is independent of the tension.
Isotropy is basically saying that the behavior is largely independent of its loading direction. And really concrete kind of is. Granted, it has different behavior in tension than it does in compression, remarkably different behavior in tension than it does in compression. And it is a very heterogeneous mixture. But if I'm building a full-blown three-dimensional finite element model of a structure, and if all I'm trying to do is assess, its global behavior, I'd probably just throw an E value and go with it. Just treat the concrete as if it behaves the same across the board. Does that make sense? Everybody else okay with that? Okay. One property that really does affect the behavior of wood, and I think this is a common theme with some of the other materials that we've dealing with, and I think you can see some of these things kind of tying together, is the moisture condition. Okay. Now, the moisture condition in a piece of concrete, or a piece of wood, is split up into either two different categories. We either define the moisture content as bound water or free water. It sounds like a very celebratory topic to bring up. Oh, what? Everybody's like, oh, now I'm going to write that down. Like on celebrations, the two different types of moisture conditions of woods. So, all right. Oh, I'm not. No, I can't. No, I'm not. So just so you're aware, when we say bound water is the water that is held inside the walls of the cells of the wood. Free water is inside the cavities. Okay. Now, the difference between the two is actually pretty significant. Number one, bound water, depending upon the level of bound water inside a piece of wood, that can greatly change the resulting volume of that piece of wood. In other words, wood can tend to undergo either an expansion or a shrinkage depending upon its bound water content. Free water just sort of flows inside the cell cavities and really doesn't do much to the volume. All free water would do in a piece of wood is increase its weight. Okay, it's just going to make it heavier. It's not going to make it bigger. Okay, so if you want to think of it like this, imagine a piece of wood as a whole bunch of really, really tiny balloons. And bound water is water inside the balloon, and free water is what's on the outside. So free water is what's on the outside, bound water is what's on the inside. So water inside the balloon is going to cause it to expand. Water on the outside really isn't going to do anything. Just make it heavier. Make sense? Okay. So just so you're aware, what is the fiber saturation point? The fiber saturation point is a lot like absorption associated with aggregates. Let's remember, what was absorption associated with aggregates? Who remembers that? Absorption was the moisture content at what state? Saturated surface dry. Now, what is saturated surface dry? What is that?
Dry to the touch.
The pores are full, but the surface is dry, right? So that's what saturated surface dry is, and that's kind of what's going on with the fiber saturation point. That's a specific moisture condition associated with a piece of wood. The idea is that the cells are completely saturated with bound water, but there's really no free water outside the cell cavities. And that varies from given species of wood to species of wood. So whether or not you're dealing with Georgia pine or Douglas fir arch or something like that, something around 21% to 32%. When you get above the fiber saturation point, all that's changing is really the weight of the wood. You're just adding water that's ultimately going to make it heavier. Below the fiber saturation point, that's, we're talking about change in water, moisture content at that state. Then we're talking about shrinking or swelling of a given piece of wood. And it really tends to change mechanical properties, et cetera, et cetera. So as your moisture content goes up, your shrinkage can change as well. So one other thing to mention, when your moisture content changes, as long as it's below the fiber saturation point, like I said, your volume's going to change, but the smallest change is in the longitudinal direction and the largest change is in the tangential direction. So what that means is the wood really isn't getting longer as much as it's getting like that. Make sense? That's sort of what's happening inside a piece of wood when the moisture content changes, as long as it's below the fiber saturation point. Another moisture content that is very important for engineering applications is its equilibrium moisture content. And that's basically what's happening when the moisture content inside the wood is sort of matching the ambient moisture content according to those atmospheric conditions in that given region. So, you know, in this region, given the moisture content in our average atmospheric conditions, EMC would be when the moisture content reaches equilibrium with our naturally occurring conditions in the area. It depends on humidity. It depends on temperature. One of the things about moisture content of wood is that it does change. It changes very slowly, and ultimately what ends up happening over time is it ends up matching local conditions and reaching EMC. You kind of have to condition lumber prior to utilization. We're going to talk about some of this stuff throughout the lecture, but we'll talk about production of lumber here pretty soon. Okay, so let's talk about some engineering applications of wood, different products. I assume everybody in here has heard of a 2x4. What are the dimensions of a 2x4? There we go. So somebody knows that a 2x4 is not 2 inches by 4 inches. Okay, so those are nominal dimensions. We plane that 2x4 a little bit in order to achieve those exact dimensions. So dimensional lumber, if you've ever heard the term dimensional lumber is defined as anything between 2 inches thick and 5 inches thick, so 2x4s, 2x6s, 2x12s, 4x4s, etc. That's used for light framing, and that owns the world in residential construction. You see those all over the place. Heavy timber are 6x6s, 8x8s, etc. And those are usually pretty rough, so when you see a 6x6, it really is 6x6, or an 8x8 really is an 8x8. You will see those for heavy framing. A big application of heavy timber is railroad ties. I mean, if you've ever seen a railroad tie, it's freaking huge, and because that's what we're talking about. You can also see it in landscaping applications. If you want to kind of pull you have a slope and you want to pull that back a little bit, you can kind of use that to create sort of a mini wall, if you will, to retain that. And then also, timber tends to be available in round stock, and I'd argue the most common application of round stock is utility poles, telephone poles, things like that. So I'm sure you all have seen your fair share of applications of wood. I don't think there's anything in this that is very earth-shattering. Yes?
You see, there's a company in Portland that's designing like decent-sized skyscrapers out of wood now.
Mm-hmm. I'm gonna you know what? Now that you're mentioning that, I'm gonna pull up a video here in a little bit. So you'll like this here. I'll pull it up later. So hold on. Okay. What's that? Yeah, I know. That's why I'm bringing it up. You'll like this. I'm going to show you a video of the largest earthquake test ever performed on a timber structure. It's big. They did a scale model. It was like 7 stories tall. Yeah. You know what? We're just going to do it now. Now, this is probably going to have some like copyright stuff on it, so I'm just going to pause the video, pause the recording. So we're back. Okay. Now, I'm curious, how many of you have ever heard of a Glulam Beam? Have you ever heard of a Glulam Beam? What's a Glulam Beam? For some of you who've heard of it. What's that? Laminated, basically. So let me ask you this. Okay, so here's an image of some, if you hear the term engineered wood or Glulam Beam, glue stands for glued laminated beam. Let me ask you this. Okay, so a laminated beam consists of basically taking different species of wood and layering them into a girder to resist loads. So let's say we're talking about this arch bridge over here on the right. Here's a pop quiz for you. Okay, if you were the designer, let's say of this bridge, okay, and you had really good, strong species of wood, and then you had not so good, kind of weak, crappy species of wood. Would you take your crappy wood and would you put it in the middle of that beam or the ends of that beam? Who says middle? Who says ends? It's the middle. No, here's what I'm getting at. So let's say you have, let's say you have some girder, and that girder is comprised of layering, different strips of wood and pressing them together in order to create a given laminated beam, right? Mechanics of materials says your bending stresses get larger on the ends than they do in the middle. So use your really good species of woods at the ends. I think I asked you all that when we did composite beams in mechanics of materials. Well, now you know. No, seriously, put your good species of wood on the ends, okay? Because in the middle, now let me say this to qualify that, on the ends, you might have to do something a little different because of shear, right? And in shear, where is your higher shear stresses? On the ends or in the middle? The middle. Your shear stress profile tends to look something like this. Something like that. So higher shear stresses in the center. Exactly. That's why you put, what are you trying to do? You're trying to increase your moment of inertia, your I value as much as possible. So how do you do that? Well, you take a lot of steel and get it as far away from the centroid as you can. So how do you do that? Well, you put flat plates like this so you can get, it's not the moment of inertia, it's that AD squared. Take it and get it far away. That's why I-beams are so stiff in their strong axis. The downside is they're very weak on their weak axis, hence why we call it strong and weak axis. So yeah. Everybody good? All right. So I'm going to pause the video again because I'm going to pull up another video. I want to talk about, I love How It's Made. It's an awesome show. If you're an engineer, have you watched How It's Made? Good. You will be. All right. So I want to talk about the production of wood products and how timber is produced. Oh, I closed it. Okay, so hold on. Okay, so the question was how are why would you sort them by their size if they're all the same size? So you all just saw a short clip on the production process from start to finish. What I sort of want to harp on a little bit is this. So what was really done in that video was really looking at combination sawing. So if we're talking about sawing a piece of wood, really there's three different main ways of doing it. One of them is plain sawing. Okay, you literally just take the piece of lumber and just saw it like this. Saw it in lengths and try and get lumber products that way. That's fine. Quarter sawing is a little more efficient. You maximize the amount of vertical cuts, but really what's done nowadays is a combination cut. And so what you saw in the video was the first thing that was done is the operator was trying to get as many 4x12s as they could out of the log, okay? And then they'd take those 4x12s and then cut them into maybe 2x12s or 2x6s or 2x4s and what have you. So really, if you were to take a snapshot of the log and then sort of superimpose what they were doing to that log, it probably looks something like this when it was all said and done from start to finish. Because the idea is, okay, let's take this log and let's literally get the most product that we can out of that individual species of log. Does that make sense? So it might have, they started out by trying to get as many 4x12s as they could, but then they took those 4x12s and turned them into 2x12s or 2x6s or so on and so forth. So ultimately, this was what happened to that log when it was all said and done. Does that make sense? That's a good question, though. All right. Anybody else? This is good stuff.
Have you seen how they timber nowadays? They have a machine that just grabs onto it, cuts it, and then rotates it, and then
Oh, the big, the one that's actually outside and collecting the specimen.
Yeah.
Yeah, it's pretty intense. It's like,
I've seen them attach the saws attached to helicopters where they just skin the tops of trees.
I've seen that, and I was in Colorado not too long ago, and I saw them doing logging. I saw the helicopter, transporting the product out. It's like, man, I hope they don't drop it. Yes, sir.
No, I'm thinking about like the material coverage and the cross section.
Mm-hmm.
Does that make a difference in like the quality?
It does, and it depends on the product. I mean, let me put it like this: you wouldn't do this for like a veneer type product, because for a veneer product, what they would do is you'd have like, let's say here's your log, you'd have a heavy roller right here, and you'd have a knife that's sort of cutting it like this and sort of shaving, if you would, a big sheet off the log. Let me also say this: if you're talking about just something like a 2x4 wall stud, probably doesn't matter. But if you're talking about an engineered product that is going to be subjected to heavy loads, then yes, that does matter. And here's another thing. It's not just how they cut it. There's also a large variety of defects in the wood that you have to account for. Things like knots, things like checks. Is it warped? Is it distorted? And all that goes into the grading process. Does that make sense? That's a good question. That's a great question. Yes. We're going to talk about those oriented strand products and laminated products here in a little bit, probably a little bit later on. But OSB, plywood, particle board, all that we're going to talk about later on. That's a good question. What's that? There is a whole different episode for that. So if you ever hear the term seasoning when it comes to wood, that does not mean the addition of paprika. Seasoning salt, shake of cayenne. So, does anybody watch Food Wishes on YouTube? Because of professors like me, right? There you go. You should be, yeah. And then you go, well, at least we're watching how it's made, right? If you ever hear the term seasoning, that's basically what that means, is that we're talking about drying. We can air dry or we can kiln dry. It just depends on what's more appropriate for a given production. Air drying's cheap, okay, but it's slow. It takes longer. Kiln drying is fast, but it's expensive. Usually there's a little bit of both. The idea is to just get the most cost-effective solution that you can. One of the things that we definitely have to assess is various defects that can happen in wood. This is a big one, okay? So let's talk about a given product, okay? So let's say I've got a log here and I've cut out let's say a given piece, and then I dry it, okay? What are you doing by drying? You're removing moisture from the product, right? What is the removal of moisture going to do to the product? It's going to shrink it, right? That's going to happen, okay? So what about this image over here up top? It sort of bowed a little bit, right? That's a defect. That's a change in the shape that we have to assess. Does that defect fall within tolerances, et cetera? So this is just to give you kind of an idea that stuff like that can happen. That's a distortion that we would have to assess. Yes. That is true. Vertical cuts tend to be the best. You tend to get more prime cuts from vertical pieces. Those horizontal pieces, yeah, you do have a tendency to get more distortion. But it's also a function of cost. If you're maximizing the efficiency of a given log, you're probably going to have some good cuts and probably going to have some bad cuts. But it also depends on what you're using them for. You see what I mean? One of the ways that we can account for some of this is through surfacing. So you all, and we mentioned this earlier, you all know that a 2x4 is not 2 inches by 4 inches because we surface that to its final dimensions. So just so you're aware, okay, surfacing takes off 1/4 of an inch, okay, for each side that's less than 8 inches originally. And if it's over 8 inches, it takes off 3/8 of an inch. So let me explain. Okay? So if I have, let's say, a 2x4, a 2x4 is actually 1.5 inches by 3 inches. And that's because given a rough cut piece of 2x4, surfacing, because it's 2 inches and 4 inches, surfacing will take off 1/4 of an inch from each surface. So if I've got the 2-inch side, right, got 2 inches, take off 1/4 inch and 1/4 inch, that gives me 1.5 inches. If I have the 4 inches, the long side, take off 1/4 inch, gives me 3.5 inches. Sound good? Now, if you have a 4x4, again, just take off 1/4 and 1/4. Now, let's say if you got a 2x12, okay? The 2x12, the 2 inches, 1/4 and 1/4 to get 1.5 inches. But the 12 inches, we take off 3/8. So 3/8, 3/8, so I get about 11 1/4. Does that make sense? Okay. Now, for my construction folks in the room, let me ask you this. What time is it? Let me see. Okay, we got this, and then we'll call it. This is a perfect place to stop. Okay, so my construction folks in the room. Okay, if you got different pieces of lumber on a given project, 2x4s, 2x6s, 4x4s, etc., what is a common way of performing estimation on the amount of lumber on a project? What's a common unit? Say it again. Board feet. How many of you heard the term board feet? That's what a board foot is. A board foot is a way of lumping your lumber product into a single unit of estimation. So let's talk a little bit about board feet. Okay. So first off, board feet are computed based on rough cut dimensions. So so if it's a 2x4, we actually use the 2x4. We don't use the 1.5. Okay. Now, what a board foot is basically a measure of a volume of wood. That's what we're measuring. So if I have a given project, the idea is how do I estimate how much wood I'm using on the entire project? Okay, we estimate that in board feet. It's just a standard unit of measure. I mean, like for instance, if we're doing concrete, we measure concrete typically by cubic yards, right? How many yards of concrete on this given project? How many board feet of wood on this given project? Now, a board foot is a 1-inch thick piece of wood that is 12 inches by 12 inches. So 1 square foot that's 1 inch thick. That is a board foot. Okay. So you might hear the term FBM, foot board measure. Might hear the term board feet. I've always used board feet. That's what I've always used. The easiest way to determine board feet is to compute your volume. Compute your volume in cubic inches, then divide by 144, because 1 foot and 1 foot. And that'll tell you how many board feet are present on a given project. So here's a simple example for you. Okay, so how many board feet, so watch this. Let's say for 30 2x4s that are 8 feet long. Okay, you want to calculate how many board feet are present. It's really simple. Okay, so we take 2 inches times 4 inches times 96 inches. There's 30 of them. Divide by 144. What do we get? 160. That's 160 board feet. Is that hard? That's simple, right? Everybody okay with that? The idea is for estimation. Like, a lot of times you're pricing wood at how many dollars per board feet. So if I need 20,000 board feet for a given project, how much is that going to cost? So it's a very common unit for estimation purposes. Board feet is something, I mean, I can almost guarantee I'm going to put that on your homework. I'm going to put that on your celebration. Make sure you can compute board feet. That's all I got. We'll finish this lecture on Thursday, and that'll complete timber. We'll do our final round of testing for concrete on Thursday. So guys, make sure you got your formula or your data sheets with you, and we'll pick that up. That's all I got.